Hello, my name is Chris Womack, and I'll be your instructor for operating systems. During class, I'll talk a little bit about myself, and we'll review the syllabus and do the logistics of Moodle and everything. Over the course of this week, you should read chapters 1, 2, and 13 in your textbook. The programming assignment number 1, is going to be released soon, hopefully within the first couple of days of this week, and it's going to be due in 2 weeks from Monday, June 5th. Alright, so let's just jump right in. So what is an operating system? The formal definition is a layer of software between application and hardware that provides useful services to those applications. Now that's pretty vague, since both applications are software and the OS is software as well. But we're going to dig in a little deeper and see what distinguishes the OS from just a normal software application. Something to note is that there are over 600 distinct operating systems at operatingsystems.org, and for one distinct operating system, which is Linux, there's over 600 flavors of Linux. So quite a bit out there. You can check it out. The link's on the slide there. What is actually common across all of these OSs? And that's the fact that they are a layer between hardware, meaning that all of these OSs can actually work on similar hardware. Here's a historical timeline of operating systems. I provided a link to the website that goes more into the history if you're interested. You won't be tested over any of this, but you should check it out. This is actually pretty cool. It's a UNIX family tree. You can check it out on the slides when you get a chance. Let's see here. So we're on, Kernel 4.10, and you can see that the family tree actually only goes to 3.x, so this is actually, it just continues to grow. Alright, so now for the meat of the lecture. So I want you to think of any of the applications that you run on your laptop or your phone. For your laptop, you have what? Web browsers, Office apps, music apps. Same for your phone, right? I mean, they got Office on the phones now, music apps, and all kinds of stuff. So all of these applications run on both of these devices. Now I want you to think about the input devices for your laptop. So we have mouse, keyboard, display. For a phone, you'd have a touch screen, right? The display is an output device, your microphone. So there are a lot of things that fit in the hardware space and a lot of things that fit in the application space. And the OS is sandwiched right in between those. So one of the definitions is an operating system is a layer of software between many applications and diverse hardware. Kind of like we said, got a lot of applications, got a lot of hardware with the operating system sandwiched in between. A more common definition, and the one that we'll usually follow, which is directly from your book, is that the operating system is the one program running at all times on the computer, and it's usually called the kernel. Now, there are 3 main things that an operating system provides. Number 1, it provides a hardware abstraction, so an application doesn't have to know the details about the hardware. This is really important for application developers, as they don't have to know the inner workings of every piece of hardware that's attached to a computer. And we'll see how this works in a moment. The second thing that an operating system does is it arbitrates access to resources among multiple applications. So this is sharing of resources. One of the most important resources is the CPU. The OS decides which application gets the CPU and for how long. The OS also provides protection. This is the third point. Using isolation, it protects applications from each other by creating their own address space to work in. I.e. processes are not allowed to touch each other's address space, and it protects the OS protects the OS itself from corrupt applications through modes, which we'll dive into in the next lecture. It also protects the hardware by limiting any one app's access to those resources. There are distinct components to an operating system, each of which we're going to dive into in depth throughout this course. Here we can see a few. We got the process manager, which contains the schedule, the thread manager, and atomic synchronization. Then we have the memory management system. We've got the file system, device manager, and there's plenty others as well. Like I said, we'll be looking at these individually throughout this course. OS components may be built on top of one another. The file system is usually built on top of the device manager. This is because the device manager, as you guessed it, manages devices. And since the disk is a device, the file system has to go through the device manager to access the disk. The file system supports a high-level abstraction, or the concept of files, and then the device manager actually handles the low-level interaction. So the file system can go through the device manager, which handles that low-level interaction with the disk. Are system libraries and tools part of the OS? This is a little bit of a semantic slide. The definition, as your book lays out, and as we defined earlier to include just the kernel, would mean that the system tools and libraries are in fact not a part of the OS. So technically, no. Since the libraries are another abstraction layer for the applications to use for system calls. But one definition of Linux, which is an operating system, is actually a stack of software, each item designed for a specific purpose. And in their definition, they said system libraries, system tools, and the kernel are all included. Now, I know I've basically said yes and no, but here's the point with this, is that the OS is, in fact, just the kernel. But the system libraries, especially glibc and the GNU core utils, are so intertwined with the kernel that they're almost always deployed as the operating system proper. So just something to keep in mind. We won't actually be testing you and trying to trick you there. All right, most modern OSs fall under the monolithic model. So we've got monolithic versus microkernel. This means that the kernel, this basically means that the kernel does a lot. Since we'll be looking at this in great detail, I'm not going to jump into really what monolithic means here. But then there's the other type of OS, which is the microkernel. And the microkernel has a minimal functionality, perhaps only a virtual memory, scheduler, and inter-process communication through messages. So the big advantage here is that it's super easy to manage, doesn't crash very often, but the message passing is very slow. And we'll see what that means as far as the distinction between monolithic and microkernel a little bit later. Mike OS X actually is a hybrid of Mach and BSD Unix. So distributed operating systems. Distributed file systems add the TCP/IP network stack to the OS. This allows remote read and writes by applications. This is actually how web servers work. On the left we have a web client, and on the right we have a web server in our diagram here. You can see that they are basically identical, with the OS handling the network hardware on each of the systems. And again, we'll cover this a little bit more towards the end of the semester. So for operating system trends, hardware has evolved very quickly and OSs must adjust. Moore's law is still applicable today, and it's doubling every 18 months. Currently, we can now get a 128 gigabyte flash drive for 16 bucks. This is a little outdated on the there at the right. Flash drive already 32 gigs at $16. And so, according to Intel, Moore's law may actually be ending in the next 5 years. They suggested that silicon transistors can only keep shrinking for another 5 years. But with quantum computing just around the corner, operating system development is still very healthy and still going to be here for some time to come. We're also seeing a diversification of OSs to many different target environments. Mobile being probably the one of the most important markets. The OS has to ensure efficient operation as well as being fast in this space. We've got multi-processors, massively parallel supercomputers, with parallelism becoming more and more important. And then we also have real-time OSs, which have been around for quite a while, but they're becoming extremely important in the area of robotics, where they're having to do a lot more than they used to. You have a normal embedded device in your home, which did very simple things like a microwave maybe, but these devices here, robots in particular, are extremely complex and need to do a lot, so OSs are having to grow there. As far as virtual machines go, this is, as most of you know, running Windows VM inside of a Linux OS and vice versa, so we have more layers of abstraction. The Windows VM running on a Linux machine has to also get to the system calls, so as you can imagine, that stack, as we saw earlier, with application on top of the OS, on top of the hardware, gets a little crazy, as the application itself has an OS with APIs and system calls of itself. So that's an interesting area for operating systems. Cloud-based computing rents VMs on racks, and this is where we're getting a lot of scaling, AWS and things like that. And so this is a huge area where we have load balancers, and we're having to grow and shrink systems quickly. So this is definitely a huge area for operating systems to grow. So here's the outline for the rest of the OS course. We're going to cover hardware support, user supervisor mode, system calls, the trap table, device input-output, interrupts, the DMA, and memory mapped I/O. We've got processes and threads, scheduling, synchronization, and deadlock, memory management, paging, virtual memory, file system design, allocation, and network file systems. We're going to look at security as well, and networked OSs as well as networks. Virtual machines themselves, I plan to get to, but we may not, so we'll have to hold out on that one and see. But if you also look at the course website, you'll get a lecture by lecture breakdown. So I'll see y'all in class.